Hi, this is Math 2510, and this video is over section 4.3, and this is part 2. I left off, I had a mistake in part 1 at the very last end, and I couldn't find where the mistake was, but I knew there was a mistake. What happened was just didn't realize there was two x's here, and so I didn't have an x squared, I have 4x. Okay, but with that being an x squared, this becomes a negative 3x squared minus 1 on the inside. And if you set that equals 0, you get complex answers. So the 2 plus square root of 5 and the 2 minus square root of 5 were not correct. And so that means that you're concave up in different places. You're concave down in different places. So these are not regions. So we only need a couple values here. So if we test with this new equation here, delete these. F of x, no, just give the second derivative. Negative 4 times negative 3x squared minus 1 divided by x squared minus 1 cubed. Now if we look at the points, we'll do negative 1 and 1. You get the undefined points. Okay, so we'll do negative 2. And you get a positive. We do 0, you get negative, and we do 2, you get positive. So there's a positive, negative, positive. So it's concave up from negative infinity to negative 1, and from 1 to infinity. Concave down between negative 1 and 1. Again, no inflection points because these are asymptotes. So they're not inflection points. So now let's move on to the next section of this. And this is called the second derivative test. Concavity provides a way to tell whether a critical point is a max or min. Sometimes. This method is called the concavity test. Oops. And we can tell the points for where the first derivative equals 0. So where your possible max or mins are, we look at those points. Point A is the local max. It occurs in a place where the derivative is concave down. So here you're concave down, so your second derivative should be, we'll call it point A, less than 0. At point B is concave up, so f double prime at point B should be greater than 0. Okay. So suppose the second derivative is continuous near C, and the first derivative equals 0 at C, and the second derivative is positive at C, then you have a local minimum. But if the first derivative is 0 at C and the second derivative is less than 0 at C, then you have a local maximum. Right, so this is concave down, gives us a maximum. Concave up gives us a local minimum. If the derivative at c equals 0, and the second derivative at c also equals 0, then the test is inconclusive. There could be a maximum, there could be a minimum, we don't know. Or there could be neither. So we don't know. Right, so we're going to take the derivatives of this function. So first derivative, we'll acquire the quotient rule. Low times derivative of the high, which is 1, minus the high times derivative of the low, which is 2x. The low squared. So this is 1 plus x squared minus 2x squared. Which is going to be 1 minus x squared over 1 plus x squared squared. And we find places where this derivative equals 0. And that's going to be at x equals 1 or negative 1. Now we take the second derivative. And we're going to have the low 1 plus x squared squared times derivative of the high, which is negative 2x, minus the high 1 minus x squared times derivative of the low, which is the chain rule, 2 times 1 plus x squared times 2x. All of this over 1 plus x squared to the fourth. Right, very similar to the one we did at the last problem of the previous video. So we'll kind of do the same thing. We'll factor out, let's see, a 1 plus x squared. So that factors out one of these. We can factor out a negative 2x. That takes into account this negative sign, that 2x. And we factor out this already, so this is taken into account. So what we have left here is 1 plus x squared plus 1 minus x squared times 2. All over 1 plus x squared 4. So we get one of those to cancel. Then in the parentheses you'll have, let's see here, this is going to be 2 minus 2x squared. We'll have 3 minus x squared. Right. Now instead of saying this equals 0, all we're going to do is find what f double prime of 1 is and what f double prime of negative 1 is. Okay. So we'll do 1 first. We'll have negative 2 times 3 minus 1, which is 2, over when 1, you get 1 plus 1 is 2, you get 8. So negative 4 over 8, negative 1 half. With negative 1, we'll get a 2 times 2. When we plug in negative 1 there, we get, that should be square, not a cube. we'll get -1, we'll get 2 cubed, which is 8. So we'll get positive 4 halves, 4 eighths. So we'll get 1/2. Alright, so again, go back up to this. If the second derivative is less than 0, you have a local max. So local max at x equals 1. And if it's positive, you have a local min. We have a local min at x equals -1. Okay, let's do the next one. We'll take the first derivative. You get x cubed minus 6x squared. Set that equals 0. So we'll have x squared x minus 6. So that would be equal to 0 or x equals to 6. Take the second derivative. You get 3x squared minus 12x. And again, we don't set that equals 0. We just plug in what we got for our first derivative being say equals 0. So f of 0 gives us 0. F of 6 gives us, let's see, 36 times 3 plus 12 times 6. So let's see, 90, 106, 102, 108 minus 72. So 28, 36, which is positive. Okay. So at x equals 6, we have a local min. At x equals 0, we do not know. Okay. We can't say it's a local min or max. We just don't know. Or we'll have to find other, and we have other ways to finding this, but this particular test doesn't tell us what the answer is. So one way we could look at this is go back to the first derivative, look at 0, and look at different points before that, -1 and 1. So if it's -1 or 1, that x squared is going to be positive. So you have a negative. If it's 1, you have a negative. So in this case, it's neither. Okay, so not a max or min. So it's not true that if the first derivative equals 0, that you have a max or a min. And so the second derivative may equal 0 and that derivative test fails. To say that it fails just means that you can't make a conclusion. And like I did, we had to do a little bit more work to determine if there's a maximum or minimum there. If you look at y equals x to the fourth, which we've seen in the last video, looks like this. There is going to be a minimum, but the second derivative and the first derivative will both be 0 as well. Right? So just because it fails doesn't mean there's not a max or a min. Okay, so we'll do the first derivative test here, set it equals 0 and solve for x. We're going to do this for x plus sine of x. So first derivative will be 1 plus cosine x. And we set that equal to 0. So we'll have cosine x equals -1. And that happens when x equals pi, or 3 pi, or 5 pi, and so on. Okay? Now we're going to take the second derivative of 1. I'm going to write this. First derivative is 1 plus cosine x. Second derivative is going to be a negative sine x. Right. And so we'll have, if we plugged in pi, 3 pi, 5 pi, we're going to end up having second derivative equal to 0. Okay. So this also wouldn't tell us, so it's inconclusive with that test. Okay. That didn't test and tell us anything. So let's go now to the first derivative test. We know pi. I'm just going to look at just the pi. You plug in something lower than pi, for example, pi over 2, you're going to have 0 here and be positive. If you plug in 3 pi over 2, you're going to have 0 here and be positive. Okay. So this means that f of x is always increasing. Which means we're not going to have any maximum minimums. If we look at the second derivative and we look at where that would be set equal to 0, and that's going to be when sine is equal to 0. That happens at 0 and at pi and 2 pi. Just look in that region for now. So if we look at, let's say, negative pi over 2, we're going to be at a negative, sine of negative pi over 2 is negative 1. So that's going to be a positive 1. If we look at pi over 2, sine of pi over 2 is 1, so that'd be negative. Look at 3 pi over 2, that's going to be sine of 3 pi over 2 is negative 1, so that'd be positive. And then we look at, 5 pi over 2, that's back to pi over 2, so that would be negative as well. So here it's switching from being concave down to concave up. So inflection points at pi, 0 pi, 2 pi, 3 pi, and so on. So if we look at this graph, x, f of x equaling x plus sine of x. And yeah, x plus sine of x. And we'll do 0, f of 0. And we'll do pi, f of pi. And we'll do 2 pi, f of 2 pi. And I'm going to change this from negative 2 pi to pi with a step value of pi. And then here I just go from negative 5 to 5. Right. And we can see, the graph becomes horizontal at the intervals of pi and I should say the odd intervals of pi. So pi, negative pi, 3 pi, 5 pi, and so on. That's where the graph is horizontal. That is why you are getting the first derivative equal to 0 in those regions. But the graph is always increasing everywhere else. Okay, I should say it's always increasing except when f prime of x equals 0. Okay. At the points where it's either horizontal or it's in between um, the horizontals, halfway in between, is where you have your inflection points. So this is concave up on the left side of 0, 0. It's concave down on the right side. As you move along, it's concave down, goes to concave up. Okay? So that's how this describes this graph. And again, I wrote up here, it's always increasing except for when the derivative is equal to 0. Alright, so that's it for 4.3. In 4.4, we are going to look at graphing functions using pretty much everything we've learned up to this point, including within previous calculus, pre-calc, and college algebra. So there's not going to be a whole lot of new stuff in this next video. I will see you then. Bye.